Cool. So there we go. The session's being recorded and I will pop it up later. So first topic back, we're talking about special power supplies. So what do you guys think special power supplies refers to?
UPS.
Yep, that's one.
Solar.
Yeah, that's another good one. Yeah. Okay, so yeah, with special power supplies, yep. So the first obvious one that everyone comes to mind is a UPS. So it just stands for uninterruptible power supply. It's a piece of electrical equipment that's designed to provide exactly what it named after, an uninterrupted supply of electrical energy to a load. So they're used in situations where a loss in supply would be detrimental. So life support, data service, critical machinery, operating theatres. The last job I did with the UPS was at Wakefield Hospital here in Wellington, where we installed two different UPS systems for the 7 operating theatres and 2 cath labs that were being installed. So it's essentially a battery that constantly supplies a load while being charged by the main supply at the same time. So the main supply is disconnected, the UPS will continue to supply the load until the battery runs out. So it'll maintain a constant supply even if the main supply is dropped, and there's no dip in voltage to the load at all. So it prevents motor contactors from dropping out or computer systems to power down unexpectedly, or any glitches in any special medical equipment that's hooked up to it. Cool. So it will protect a critical essential load from the following types of faults. So blackout. So there's a complete blackout, transformer goes down, network goes down, the UPS will keep going for as long as it's rated to. So depending on the type of system it's supplying, you'll get an adequately rated UPS. Just while we're talking about it, has anyone managed to complete their UPS on job? Just post in chat, yes or no. Yeah, I figured as much. When I did my apprenticeship, my company just had us come to the workshop and we did a kind of benchtop UPS install because it just has to be, I believe, from my memory, 3 kVA. So it can be one of those benchtop ones for computers. But yeah, if you are having trouble with that, please talk to your mentor, and ETCO, whatever region you're in, ETCO will try and help you along with that. Cool. So brownout. So a brownout is where there's a reduction in voltage but not a complete loss. So it's when a piece of equipment or installation draws a heavy current, it'll cause significant volt drop on the system. The system becomes too loaded, voltage can drop beyond what equipment is designed to operate at. Typically short-lived, as they usually happen when a large motor starts and draws excess current, but can cause trouble for sensitive equipment, or it can be caused by a fault in the transformer at the street. I've had a couple of call-outs early on in my career where customers complaining that their lights were dim and their power points weren't giving enough power. Turns out the transformer at the street had a fault, and Wellington Electricity were going to replace it but hadn't yet. And voltage surges and spikes. So a surge or spike is a sudden and short-lived increase in voltage, greater than was typically expected. These can be caused by lightning strikes or large inductive loads being de-energized. So backfeeding from motors, and sensitive equipment can be damaged by a surge in voltage, even if it's only for a fraction of a second. So you'd also use surge protection to protect against this. But yeah, if you've got like small motors, if there's a spike in voltage while it's being run, it can burn out the windings just because the windings are so small. Cool. Noise and interference. So this is when voltage waveforms has irregularities riding on it. So when there's noise and interference on a line, the sine waveform is altered and misshapen. This can affect sensitive equipment such as computers, leaving files corrupted and software malfunctioning. Cool. So how do they work? So in a nutshell, a UPS takes an unconditioned AC supply and rectifies it into DC. The DC is then used to charge the batteries and also converted back into AC supply to supply the load. As it's converted back into AC, it is conditioned so provides a clean output. A bypass is also offered if there is a failure with the UPS itself. Cool. So the diagram below, you've got the supply. Here's your rectifier. It says inverter, but that's wrong. It's a rectifier. We've got your battery. There's your inverter back to AC. Your bypass switch and your load. This is the basic circuit for a UPS. Yeah, you've got your supply, your rectifier, not your inverter, and then that feeds a battery as well as going to the inverter, which then feeds the load, and a bypass so you can just bypass the entire circuit. Cool. So online versus offline. So an offline UPS, the system feeds the load via the static bypass in the first instance. It will provide a degree of filtering to improve the power quality and energy through normally closed contacts of the static bypass switch and onto the critical load. The UPS system also takes an amount of electrical energy to maintain charge on the batteries and monitor the supply. If the supply is lost to the load, the static bypass switch rapidly operates, so usually within 10 milliseconds. There tends to be a small enough gap for computer systems to still maintain a small amount of charge to continue operating. So got some different components here. So you've got an EMI filter on the supply. So it feeds a static bypass, which is normally closed and then goes to the load. And then you've got your rectifier, your DC filter, battery, inverter, another AC filter, and the static bypass, normally open contacts. So yeah, when the static bypass triggers, because there's loss of supply, normally closed contact opens, normally open closes, and the battery begins to feed the load. Cool, and then you've got your online UPS. So the most basic way to compare an online UPS differs from an offline one is that the static bypass switch contacts are the opposite. An online UPS constantly runs the supply through it and out to the critical load. This type of UPS is constantly converting the supply into DC, charging the batteries, and then recreating the AC supply. While filtering and conditioning the waveform, this means that the batteries are constantly in parallel with the load, and if there is a loss in supply, the batteries are already in circuit and continue to supply the load. In this case, there is no momentary loss to the load, so there's no loss of power. When the power cuts out, it's just like nothing happens. Cool. So some things to know about UPSs. They are fucking heavy. So even a small UPS can be very heavy for its size. Because the majority of their construction is battery, their weight can be very deceiving. It always pays to identify how heavy the device is before you attempt lifting it. So they're toxic. The contents of the battery held within a UPS are more than often toxic. For this reason, care must be taken when working with the battery parts of a UPS. It's not common yet for them to be lithium ion. It's more common for them to still be lead acid batteries in large scale UPS units. They're generally only lithium ion in the smaller desktop versions, not versions. So they're fragile. A UPS must be installed and operated in the ways stated by the manufacturers. Often there are environmental conditions that must be considered for the long-term health and longevity of the UPS. They are electrical. Correct installation operating procedure must also be adhered to. For instance, always connect the UPS to the supply using a supplied cord and/or plug. If it does not come with a cord set, consult the installation instructions on the best way to connect the device. Yeah, UPSs, they're great, but they are quite hazardous and they take care to install. It's why they have included the sign off in the curriculum, because they are something that should be installed by a qualified and competent person. To be fair, more often than not, in a large scale UPS for like a hospital, you will have the electrician do some of the work, but you'll also have a UPS installer from the UPS supplier come and do some of the work alongside you to make sure it's been done correctly and as per their manufacturing instructions. Cool. I believe this is a video.
So what is a UPS, or uninterruptible power supply? An uninterruptible power supply is a device that is used to keep computers and equipment safe when there is a loss or significant reduction in the primary power source. To achieve this, the UPS houses several batteries that take over when it detects a loss or reduction in available power. Once this is detected, the control is transferred over to the batteries, and via an inverter, the battery's DC voltage is converted into AC for the devices. In reality, it doesn't have to be computer systems and equipment that are kept alive by UPS. It could be anything from a fish tank to a foot massager. We aren't just talking about plain power outages, lights off, TV off, everything. But we can sometimes get spikes in power where a sudden drop can assure our devices are momentarily powered off, or something known as a brownout. This is where there is a voltage drop, either unintentionally or intentionally. Sometimes in an emergency, there is a load reduction caused intentionally. With a UPS, all of our systems can run as normal to compensate for the reduction in power. Clever. Before we get started on today's video, if you love our videos, be sure to click the like button below. Then make sure to click subscribe and the little bell to receive notifications of new RealPARS videos. This way, you never miss another one. The amount of time the UPS can sustain a system for can vary, but it allows the opportunity for the issue to be resolved, or at the very least, allows for the systems to be shut down in a controlled manner. Even the simplest UPS is made up of a number of parts. We're going to look at the standard parts that you can find in a basic UPS system. Since a UPS is a system that uses batteries to power a system, should the supply be compromised, we of course have batteries and a battery charger. Since the batteries use DC current, and our incoming supply is AC current, we need to convert DC to AC using an inverter. Finally, we need a way of switching between the AC incoming supply and battery power. For this, we use something called a transfer switch. So, to break it down, these are the parts we need for a basic UPS system: batteries, battery charger, inverter, and transfer switch. A UPS provides second-level surge protection, but although it does provide some protection, it should usually be used alongside an adequate surge protection device, or SPD, to extend the life of the UPS, as well as the attached equipment. Sounds simple, right? We've already discovered a basic UPS system and what parts it includes. Now, we're going to find out all about the different types of uninterruptible power supplies and what their typical functions are. Firstly, and the most common in smaller systems, is the standby or offline UPS. This is the one you would normally use on a personal computer, for example. The standby UPS lays in wait for its time to spring into action, and once there's a power failure, it takes control. The standby UPS tends to be the most cost-effective UPS available. Next up, we have the line interactive UPS. You'll find this type of UPS in small business infrastructure. It is very similar to a standby UPS, but with the added ability to regulate voltage automatically. This means that it monitors the incoming supply and can help out if it detects that the voltage is a bit low or a spike is causing it to go too high. It can add or subtract power in this way to make the output to our devices constant. Very smart. This type of UPS is particularly useful for the brownout situation we've already mentioned, or power spikes or surges. Now, we have the online double conversion UPS. Don't let the name put you off. This type of UPS is efficient as the primary source of power isn't the incoming supply. Rather, it is the battery power. So when we have a power outage, there's no transfer switch to close, meaning no time to switch that you can get with the other type of UPSs. When the incoming supply is on, the batteries simply charge up. It's called a double conversion because it converts the AC incoming supply to DC, and then the inverter converts it back to AC for the output. In general, it ensures a far higher degree of isolation of the load from the irregularities on the main supply. These are the most common types of UPS available. Of course, there are other types that fit a particular form or function, but these tend to be for more specialist needs. In summary, today we've learned about uninterruptible power supplies. We've learned that they can be used as a backup to mains power in an emergency situation, such as a power outage. More advanced UPSs can regulate the voltage to prevent damage to equipment in case of a brownout or a power surge. We now have a good understanding of what parts are used to make up a UPS: batteries, a battery charger, inverter, and a transfer switch. Finally, we know that an online double conversion UPS is the most efficient, as it doesn't need a transfer switch as the primary source of the power goes through the batteries. That's it for this video. I hope you enjoyed learning about UPS systems, why we use them, and what they're used for. Okay, that's all.
Cool. So, yeah, so that's a good video to reference. So this is an example of, yeah, it is. This is an example of the one of the UPS systems that I was talking about for Wakefield Hospital. So if you see on the left photo there, so those five units there are considered one UPS unit. So you've got the top, which is the UPS control and power delivery system, and then you've got the four on the bottom, which are external battery units, and they're basically a boost for the top unit. So in that rack on the right-hand side, you've got three different UPS units, and each of those, one of those is for one operating theatre. Originally, they thought that's all they were going to need for the operating theatres, and then they realised actually they needed more. So then they ordered this system. So on the right there, those are the kind of more traditional lead acid batteries that people think of when they think of a big old school style UPS system. In the middle there, that's one of Eaton, because Eaton supplied all of the, well, it was an Eaton-based system. That's a DC breaker for the batteries. And then on the left there, that is a more traditional kind of UPS control unit, which is hooked into all of those big lead acid batteries. And then this is two different types of UPS alarm panel. So you've got the one on the left there, which is for the first type of UPS that we were looking at. And then the one on the right there is for the other one. So the one on the left there will tell you if it's been bypassed or if it's just got a fault. But the one on the right is just a UPS, is a fault alarm. Yeah, there's a lot of different features depending on the UPS that you buy. Sometimes they have a Ethernet connection, so they connect direct into all of your computers, and then they tell each of your computers, hey, I've switched over to UPS, save all the documents, and then slowly start to shut down all your programs and power down before the battery runs out, depending on the size of the UPS, or maybe it'll tell it, hey, I've gone to UPS power, and then after half the battery is drained, okay, now it's time to save everything and shut down. And I don't know if they cut those screws afterwards. I hope they did, because they're a bit long. Thanks. Right, so just attendance question. Okay, so I've been doing a bit of poll of the apprentices we've had here on block course. What's your go-to screwdriver brand?
Weha.
Oh, okay, I was gonna say, it looks like we've all got Weha. Swift Tools, Craft-Rite at the moment. Oh shit, sorry, Dara. Milwaukee, yeah. How you finding the Milwaukee ones, Chris? I just got me a set and I'm curious. I haven't had a chance to try them out yet. Yeah, I will say, don't get the Klein ones. I had the Klein ones for about a year and a half, and all of them were bent. Yeah, all of my Klein screwdrivers bent, and I was not happy. Cool. So another type of special power supply is a standby generator or a genset. So it's like a UPS. They sit in the background waiting to be used, and when the main supply is lost, when the main supply is lost, it turns on and kicks in. Main one being a UPS, essentially a battery, and a genset is an engine. There are more subtle ones though. So a UPS is relatively quick to act in a power failure, especially online UPS because it continuously supplies power. However, a genset takes a few seconds to initialize and provide energy at a set voltage and frequency. It says a few seconds, but depending on the genset and how big the genset is, it could take anywhere from 5 to 30 seconds to fully kick in properly. Although maintenance is required on a UPS, a genset requires more as there are more moving parts and intricate pieces that require more attention. And a UPS requires an electrician or someone who's at least competent, whereas a generator is more kind of your mechanic or your engineers doing the maintenance, as well as us, because we have to make sure contacts are clean, it's putting out the right voltage, all that kind of stuff. They can supply a huge amount of power in relation to a UPS. A single genset can supply backup power to a large section of factories and plant, of which a UPS just couldn't do that. Especially some of the bigger standby generators, they can leave them hooked up to the supply of a street for days or weeks at a time, as long as you maintain the fuel level inside that genset. In saying this, a UPS system and genset are often seen running in tandem with each other. A large essential piece of electrical equipment may be supplied by a UPS in the first few seconds of a blackout while the genset is starting up. And then once the genset is started properly, it takes over and the UPS is disengaged. So some gensets need to be manually activated. However, ones that are responsible for critical and essential loads typically have a relay built in that monitors the main supply. And if it's lost, automatically starts the backup. Some also run weekly tests on themselves to ensure operation, and they often run on diesel, natural gas, or LPG as a fuel source. So the systems at I'm just using Wakefield Hospital as my constant reference because it's what I was most recently familiar with. All of the computer systems and operating theatres have UPS backup, and then they have 2 CAT generators. For reference of size, they sit inside 2 shipping containers on top of a hill. So that's the size of the generators they've got. And then the main switchboard has a PLC controlled breaker system so that as the generator comes on and starts to provide power, it will slowly bring on different loads for different areas of the hospital, starting with most critical to least critical until the generator is fully loaded, and then it will not provide any more power. So that way they know computer systems, operating theatres, the ICU, the cath labs all have power before they start bringing power on for the patient areas where there's less critical patient, or the smoker room for the doctors. We called it the theatre lounge. They'll also make sure the mechanical and air scrubbing units for the operating theatres have power before any of those less critical areas as well. Cool, so you got permanently fixed. So permanently fixed generator systems can be very large and designed to offer a great deal of electrical energy. Large sites with essential service often have permanent backup gensets, such as factories, hospitals, and high-rise buildings. Some of these fixed systems have a reticulated fuel source connected to them, such as a natural gas line. Others have a tank of stored fuel like diesel. These types of generators are very reliable and with regular maintenance run for years with no issue. Due to their size and output, though, they can be extremely loud, so need to be located in areas where noise will not affect the surroundings, and hearing protection is needed by those that work on them. And then you've got portable. So this type of generator is relatively small. Some can be carried around by 1 or 2 people and supply enough energy to run a small residence. Other can be brought in on a truck or trailer. Either way, they're designed to be portable and ready to go on site when backup power is required. These ones tend to have a tank to store fuel, and precautions must be made when transporting equipment with stored fuel inside. Because of their size, sometimes they can fit inside an enclosed space. However, they must be well ventilated as exhaust fumes can accumulate rapidly. Anyone here do maintenance or like retrofit residential jobs? Actually, what fields are you guys working in? Are you guys working in residential, commercial, industrial? Yeah, commercial. Yeah, at least one resi. Oh, cool, industrial, nice. Oh yeah, mostly residential, little commercial. House bashing. Nothing wrong with house bashing. Okay, yeah. So I've done state housing maintenance and commercial new builds and a little bit of residential new builds. So back when we were doing state housing jobs, sometimes the tenants would have certain loads that couldn't be left off. Like sometimes they were in state housing because they had medical issues and they had like a CPAP machine or a breathing machine, or I think the weirdest one we had was a liquid antibiotic nebulizer. Basically, it took the liquid antibiotics, nebulized it into a steam so they could breathe it in. But either way, they needed power while we were upgrading their switchboard, or they'd lost, we had to replace their mains. So we would bring in a portable generator for them to plug their critical loads in. And we'd always make sure to transport it with half a tank of gas or less, because any more it would just slot around inside and probably leak out. So always be cautious when you're transporting them. So the components of, you've got your engine, you've got your alternator, Got your fuel system, voltage regulator, cooling and exhaust, and lubrication system, and the battery charger as well. Control panel, and the main assembly frame. Yeah. Engine, alternator, fuel system, voltage regulator, cooling exhaust, lubrication, battery charger, control panel, and your main assembly frame. So these are the different parts of your genset, especially the one you could say the main assembly and frame. You've got one in this, got it in the smaller ones, but there'll always be a battery charger because you need most of them need a battery to start and keep running. I mean, some of them will probably still have the good old pull start, but most of the ones you get nowadays have the electronic starter, and sometimes they'll just have the pull cord as a backup. Cool. So this is a Cat diesel generator. There you've got all the doors are openable and accessible. That's your control panel. That's quite loud. That's your control panel with an e-stop. All the doors are openable for accessibility. You've got your battery storage there, your cooling fan. That's your alternator in there. Door system to allow the fumes out. As you can see, it's quite quiet with the doors shut. So you can leave it, it's only 93 dB. Yeah, looks like oil intake there, probably a dipstick somewhere. Fuel filter up the top, oil filter down the bottom. Yeah. See there, it's got a speed rating, how long it's been running for, output voltage, load current. Gensets normally have a system on them for letting you know how many hours it's run for, because that gives you, because it doesn't matter how old the genset is, it just matters how long it's been run for, because the genset could be, 5 years old or 10 years old, but the 10-year-old one may not have been used as much, so it's only got a couple hundred hours on it, whereas the 5-year-old one could have had 500-600 hours on it because it's been used continuously. Also safety with gensets. So you've got the exhaust fumes. So all combustion engines emit gases and fumes that are toxic to our health and environment. Diesel generator will emit both carbon dioxide and monoxide. So use them both outside. It's not always possible, but always make sure that if they're used indoors, you use proper fans. Oh, cool. So you do a lot of solar. Nice, mate. Yeah. Gases everywhere, and sensors and alarms must be used to detect, monitor, and alert people to high levels of dangerous gases. So yeah, it's always better to use it outside, but I know sometimes it's not always possible. And noise. So large gensets also produce large quantities of noise. So when you're working around the generator, you must wear appropriate hearing protection so that the noise level will not impact us. When we're working around generators, it is wise to wear hearing protection even if it's not running. If a power loss occurs, the generator may start automatically and you may not be able to move away from it fast enough. Cool. So large generators have the potential to supply thousands of amps. So you must be careful when working on or around gensets so the levels of prospective short circuit current is allowed for. Appropriate circuit protection must be used, as well as effective barriers and separation techniques. Generators must not supply the house in such a way where it can be connected in parallel with the main supply. This can cause serious safety risks for anyone working on adjoining systems, as is a dual system of supply. The genset can also be damaged by the incoming supply. Standby generators should never be connected on a temporary basis to the electrical circuits in the premises. To do so could endanger the premises occupants, neighbours and network workers. Manufacturer's instruction must be adhered to in respect of what loading can be connected to the gensets and earthing requirements. Yeah, that is a pretty key thing. So you guys may remember the massive storms, hurricanes and flooding we had up north, and there was a lot of damage to the electrical network. One of the things that residents were told was that they shouldn't be turning their solar systems on or having their solar systems on, because they were worried about a risk of backfeeding the network. And obviously, if you backfeed the network with a generator or with solar, and there's someone working on the lines, there's a potential for people to get shocked. Has anyone ever worked on or seen a connection point for generators into a domestic installation? So like there's a plug for the generator to be plugged in the event of a power outage. Oh yeah, nice, with a changeover switch. Yeah. So if you, because some people in New Zealand, more common over in America, they'll install a special socket outlet to hook up a small temporary generator, but they have to install a transfer switch or some kind of transfer system, so that way they don't have the mains connected at the same time the generator's running. So like if the power's out because of a storm, you can flick the transfer switch, plug in the generator, start it up, and it'll power your house. You just got to make sure you only turn on the loads that it can actually handle. Cool. So regulatory, as well as safety requirements to be adhered to, there are also legislative requirements that we must be aware of and work within when working on gensets. So a licensed electrician must be the one to install the generator and work on any wiring related to the generator. The connection of the generator must be made on the installation side or load side of any revenue meters. This is done so that the meter does not calculate any energy being applied by the generator to the installation. Loads must not exceed the maximum load rating of the generator. If the load rating is exceeded, it can cause damage to the generator and auxiliary equipment. Usually on the generator, it'll have basically a load percentage. So it may be capable of running 2,000 kVA, or sorry, 200 kVA or something like that. But it's what might have a say only run at 85 or 90% load for safety reasons. Changeover switch must be fitted so the genset cannot be connected in parallel to the main supply. The switch can be a manual or automatic type, but must effectively isolate the genset supply from the main supply backfeeding. So one way to do this is to have a no voltage relay and contactor set up, or changeover contactor. So that way, if the mains are connected, the contactor either stays open or stays closed to allow the mains to run through. But then if the load drops out, then the contactor releases and then transfers the power over to the generator. Or just a big transfer switch. Gensets that start automatically must be tested, maintained and serviced regularly by a specialist company so that in the event they are needed, it can be assured that they will operate correctly.
G'day. Probably hearing more and more about Australia's energy crisis. Residents in South Australia certainly know all about it. Last summer, they had 3 major blackouts. Some people losing power for over 3 days. Now millions more of us are being told to expect power shortages, extended blackouts this summer.
I'm sorry that it's an Australian video.
Your home or business to make sure that you have access to power even when there is a blackout. Good quality generator is a reliable and affordable way to do just that. Today we're going to talk about just how easy it is to connect your home to a generator using a manual transfer switch. Why would you use a manual transfer switch? Well, without one, if you've got a generator, you can always run an extension cord into the house and power portable lights, appliances, power boards and extension cords. But things quickly become complicated and potentially dangerous with things lying around all over the place. But when you add a manual transfer switch, all you have to do is plug in the generator to a single outlet outside the house. Then you'll have fixed lighting, power outlets, and all your appliances as normal, including hot water units and air conditioners. Now, Silvano here is the Sparky who hooked up this home in Whittlesea. Tell us, Silvano, how easy is it to set one of these up?
It's very simple to install a manual transfer switch. In your switchboard, you just need to install a appliance outlet outside the building. When you lose power, your generator will be plugged into your appliance outlet. You'll come back to your switchboard, change your switch from mains to generator. You are on generator power, and you plug in whatever appliance you need to power your house up.
Easy. Now, is this the kind of thing that any homeowner can install for themselves?
No, legally, you're not allowed to install it yourself. You must have a licensed electrician to perform any electrical works anywhere in Australia. He will give you the information that you need to install the required equipment.
Great. And how expensive is this sort of thing?
Generally not. Your licensed electrician will give you a quote on your application. He will view your switchboard, he will view your surroundings, and he will give you a quote upon that.
Easy. So there you have it. The whole house up and running in under 2 minutes. Making sure you've got power is that simple and easy. Just make sure you always use a licensed electrician.
Yeah, always make sure you're using an electrician to install stuff like that. Good future job for you guys. This is just going over the different parts of the setup for your transfer system. You'd normally have a fuse, not an MCB coming, and that'd normally be on the pole. One of the few situations where it would be advisable to have neutral switching, because when you're having a gen set system set up like this, you need to completely disconnect the neutral when you're changing over from the main supply to the generator supply to ensure you don't backfeed the network through the neutral. Yeah, the relay there is being used as your no voltage relay. And that's going to the starter switch in your generator. Yeah, because there's been an interruption in power, the commons have to normally close, and then that activated the generator and activated the second contactor. Yep, utilities come back on, the generator ignition system's been turned off, contactors have switched over, and now you're back on the main supply. Yeah, so it only works for the electric startup generators. So yeah, that's the way you normally would set up a generator like that. Obviously, if you were using a manual setup because yours is a plug-in, you'd still have to have that either changeover switch or contactor setup just to ensure that if you have the generator running and all of a sudden the main supply is brought back on, it will interrupt the generator supply. So that way you're not backfeeding the network. Cool. So you got your different types of loads. So you're not essential loads. So the loads are just that. It's nice to have, but you're not going to require them. You know, if you have them, don't have them on, it's an inconvenience, but it's not going to cause you any ill effect. So it's not a necessity to keep these loads going. It only adds unnecessary strain on the backup power supplies. So when these supplies can be used for higher priority loads, so things like general lighting and socket outlets, your cooking appliances, or your air conditioning. Although some of us would argue in the height of summer, air conditioning is definitely essential. So you got your essential loads, so the loads that need to continue supplying with power, even if the main supply drops out. They can suffer a short drop before being repowered again. The load category is often supplied by the main grid supply and a backup generator. why the loads can be maintained, but usually there is a slight changeover period. So they're your emergency lighting systems and your elevator systems. Although a lot of elevators these days also have a battery backup system installed, mostly enough to get the elevator from between floors to the nearest floor. And that's what they're set up to do. As soon as they detect that the mains has disconnected, the battery will kick in and it'll take the elevator to the nearest floor, open the doors, and let you out. Critical loads. These are loads that cannot lose power under any circumstances. So yeah, the only way to achieve that is with a UPS system. So an online UPS will continue to deliver power, even in the event of a main supply loss, as it's connected in parallel. This keeps the load constantly powered until a backup genset can be brought on to supply power. So medical installations and life support systems, and your fire protection system. So normally your fire protection systems also have a battery built into them. If you open any of the fire panels that you see in commercial buildings, you'll find a small, it's not car battery, but a small battery inside of it. It's about the size of, say, 4 batteries for a drill, 4 drill batteries, yeah. Or a couple of the big chunky DeWalt ones. Cool. So non-essential, essential, critical. Cool. The next one we'll look at is switch mode power supplies. So a switch mode power supply is an electronic piece of equipment designed to adjust the power output to a particular load. There are many different types of SMPs. And it can be very easy to become overwhelmed by the technicality of them. But let's look at the basics. There are 2 broad ranges of power supplies when stepping voltages up and down to supply electrical equipment, linear and switch mode. So linear, in relation to what we are learning, a linear power supply has a linear relationship between its input and output. A simple AC to AC step-down transformer will offer voltage that is proportional to its input due to the turns ratio of the transformer. For example, 230-volt transformer might typically offer 24-volt on the secondary, but if the supply voltage is decreased to 210-volt, the output then becomes 21.9. This type of power supply has its advantages and disadvantages. The advantage, they're cheap, and they have relatively simpler construction compared to an SMPS. They also do not introduce noise into the output circuit. Disadvantage, they aren't very efficient when it comes to losses through heat. They can also be large and cumbersome as their rating increases as transformer sizes increase, as well as heat sinks. And then you've got switch mode power supplies. So the first step in SMPS is a rectifier. This converts AC supply into DC, done through diodes that only let current flow in one direction. Filter components such as capacitors and inductors are used to condition the waveform from a pulsating DC waveform to a smooth, even DC supply. You guys have already gone over capacitors, inductance, and power factor. Once the smooth DC has been achieved, it is rapidly switched on and off to alter the overall output supply to the load. This is done using a technique called pulse width modulation. The electronic circuitry detects the input and references it to the desired output and adjusts the rate at which the device switches to achieve the desired output, along with some additional filtering. This rapid switching can be done at very high frequency compared to the input AC frequency. Some SMPS devices operate at tens of thousands of hertz. Now that the signal is being switched on and off rapidly, it almost resembles an AC waveform again, only at a much higher frequency and with square faces rather than a smooth undulating one like pure AC. This can now be transformed and rectified again to achieve a close to perfect output DC waveform. The advantages, because of the rapid switching technique to achieve a lower overall output, they do not require components like resistors to create a volt drop, which leads to heat. This makes them much more efficient Also, because they do not generate relatively large amounts of heat, there's no need for large heat sinks, so they can be made a lot smaller than their linear power supply counterparts. They contain components like capacitors that store charge, so they can be dangerous to open even when disconnected from mains. They also create noise and interference in lines due to the high frequency switching. This can cause issues with telecommunication devices.
Which means switch mode power supply. This is one of the most commonly used supply with a relatively high efficiency. An SMPS transfers power usually from AC to DC and converts voltage and current characteristics as needed for a specific project. The opposite type of supplies are those who are using linear regulators and transformers. These are not efficient at all and also could be very big and weigh too much. As you can see here, this is a 10-watt switch power supply, and it only weighs 50 grams. Now this here is a 30-watt switch power supply and weighs around 100 grams. But now this one here is just 18 watts linear power supply, and it already weighs around 4 times more than the other supplies. And also another compare, this is the PCB of a 360-watt supply of 24 volts and weighs just below 400 grams. But now we have just the transformer of a 50 watts linear power supply of 12 volts, and it already weighs double the weight, but is for 7 times less power. The costs are also higher due to more material needed to fabricate for the metal and the copper wire. And also for higher loads, we need a lot more copper wire and also a lot thicker. But as you can see, the circuit is a lot more complex for the switch supply. So how can this be cheaper, have more efficiency, better range for the voltage, weight less and be smaller and smaller than the common transformer and linear regulator supplies? Well, in this video, I will tell you step by step how a switch mode power supply works. We will go through all the components that you can see on these PCBs and explain you why we need each one, and by that you will learn the process of a switch supply. So guys, make sure that you subscribe and activate the notification bell. And also consider supporting me on Patreon. So let's get started. This episode is sponsored by the PCB manufacturer company GLC PCB. Their main services are the 2-layer PCBs for only $2. Also 4 and 6-layer PCBs, the SMT assembly process will look at the PCBs with all the components already soldered in place, and also the SMT stencil for soldering SMT components with solder paste. The quality of the PCBs is amazing. I use their services all the time and always get good results. For only $2, you have 5 PCBs of any color that you want. So go to glcpcb.com, upload the Gerber files of your design, and order the PCBs in just a couple of minutes. What's up, my friends? Welcome back. This is a so-called linear power supply. In order to understand why the switch supplies are better, we need to know what is wrong with the linear supplies. I guess that you already know, but the linear power supply uses a transformer to lower the voltage from, let's say, 230 volts AC to something like 20 volts. Then we use a full bridge rectifier to get DC voltage. And finally, we apply a simple filter made with a capacitor. It's also quite common to add a linear voltage regulator at this output, so we could get very stable values for, let's say, 5 volts, 12 volts, 24, and so on. We do that because the transformer ratio is not always perfect, and the high voltage input is not always the same value and 100% stable. So what is wrong with this setup? Well, it has a lot of power losses, weighs too much, and is expensive, and for high loads is not a good option. A part of the power is lost on the transformer, and even more power is lost on the regulator, because as you all know, linear regulators are not that efficient, and usually they lose power in the form of heat. So first of all, these transformers work at low frequency, such as 50 or 60 Hertz, because that's the frequency we have on our home outlets. And remember that the coil impedance is proportional to the frequency and the self-induction coefficient. So 50 or 60 Hertz is a very low frequency. So if the frequency is low, the self-induction coefficient must be high. To achieve high values of self-induction coefficients, we need to use metal cores, which are very heavy. And at the same time, we must create the winding with a high number of loops. So more weight together with more loops, so more copper, will result into a heavy, big and more expensive transformer. And even more, if you need to supply high loads, the copper winding of the transformer must be a lot thicker, obviously, in order to be able to handle high current. So that will make the transformer even bigger, heavier, and cost a lot more. But on the other side, switch power supplies will work at very high frequencies, higher than 20 kHz. Even more, this can work with square signals. High frequency square signals will let us work with much smaller transformers, which can weigh a lot less. We use these so-called pulse transformers, which usually will have a core made out of ferrite to reduce the losses due to eddy currents. We achieve the high-frequency square signals with the use of 4 MOSFET transistors. These work in commutation mode, so we reduce the dissipated power. That's because a MOSFET will dissipate small power when in saturation or cutoff mode. It only dissipates a lot of power when we switch from saturation to cutoff or from cutoff to saturation. So that's how we can get an efficiency a lot higher than linear power supplies. Less weight using small transformers and a lot more power, because the output can now have thicker copper wires that don't have to be that long. With a thick copper wire, we can regulate the output and also have a decent current value. But this will come at a cost, because the circuit of these supplies is a lot more complex. So let's study the schematic of a basic switch mode power supply. These supplies would usually have 5 parts, as you can see here from A to E. A is the main input protection and filter. B is the full bridge rectifier, together with the primary filter of the supply. The C part are the switching transistors, and usually we use 2, but sometimes it's just 1. Part D is the transformer, which this time is a lot smaller than a linear power supply. Together with this transformer, we have the second rectifier's diodes. And finally, part E is the output filter coil and capacitors, and also the feedback. Now let's talk about each part separately, starting with block A.
Okay, that video is getting a bit long. If you guys want to read up in more detail about the different components in the special power supply, you can look through the learning resource on Moodle. I'm just aware that we have to get through all of the information tonight because we were supposed to have 2 weeks on special power supplies, but we obviously lost last week to Waitangi Day. So yeah, we'll move on. So solar. So solar is another type of special power supply. You've got your, some of you may be familiar with, you've got your solar PV panels, your DC isolator, your DC AC inverter and battery storage. You've got your AC isolators, AC cabling, switchboard, kilowatt hour meter, and your connection to the grid and sub-circuits. Okay, so also with solar, yep, you've got the DC AC inverter and the battery storage, but you also sometimes have micro inverters behind every solar panel on the roof. These are becoming more commonplace from what I'm being told by some of the guys in the industry, because it means that you can have smaller cabling down inside, and you don't have to have one big AC inverter downstairs. It makes it a lot easier for, and then you just need you still need an AC inverter if you're going for the battery storage. But if you're not using battery storage, micro inverters. What's this one?
So here you can see an example of an off-grid system. And as you can see, the system consists of several components, and I'm going to introduce each in this video. Let's start with batteries. Batteries store the solar energy. Solar batteries work by storing the DC energy being produced by solar panels and giving it back to you when you need it. There are different types of batteries used in solar systems, and you can choose them according to your specific requirements. Here, the batteries are connected in series with each other to increase the voltage of the system. Each battery has a positive and negative terminal, and you can connect them in parallel or series to change the voltage and the capacity of your off-grid system. This is the charge controller. It manages the power going into the battery bank from your solar panels. It also ensures a healthy charge profile for the batteries and stops the power running backward to the solar panels overnight. Typically, charge controllers come with two technologies: the maximum power point tracker, or MPPT, and the pulse width modulation, or PWM. And this controller is an example of an MPPT charge controller. This is the inverter. Inverter converts the direct current or DC output of the batteries into the alternating current or AC, which enables you to power your AC equipments with the use of batteries. This is the monitoring device, which will be connected to the charge controller and is responsible to provide you with information about your solar set, such as voltage, current, power, temperature, and so on. DC and AC breakers provide methods for us to stop current and voltage being supplied to the equipment. So when we would like to remove or service those items, or in the event of an overcurrent, they come really handy. Solar panels and batteries are the DC sources. Therefore, DC switches are used for solar panels and batteries. The AC switch is connected to the inverter's output and protects the inverter and consumers in case of abnormal conditions. So, using the AC switch, we have the control over the AC output. Okay, there are lots of connections here. Let's find out how to wire the off-grid system. Two connections come out of the batteries, one from the positive terminal and the other from the negative terminal. Battery positive goes to the charger's positive battery terminal, and battery negative goes to the charger's negative battery terminal. The bus bar makes it possible to split the connections. This means that the positive is connected to two places and the negative is also connected to two places. Then the negative connection once goes to the charger and inverter, and the positive goes to the charger and inverter. This is called the rail or DIN rail, which is a metal strip that is used for securely attaching electrical and industrial control products such as circuit breakers or thermal blocks, and here we mounted our switches on it. Okay, I'll remove the cover here. Here I have the PV positive and negative terminals, battery positive and negative terminals, and DC loads positive and negative terminals. Turning the DC switch on will connect the batteries to the charge controller and will turn it on. As you can see, the charge controller is on and is displaying some parameters on its LCD. Turning the other DC switch on will connect the solar panel's positive and negative terminals to the charge controller. Now I turn the inverter on, and turning the AC switch on will bring the power to the plug. So I plug an AC consumer like this drill, and it will let me use my AC equipment. In next videos, we will talk about each component in more details.
Yep, so that's a solar setup. So another type of, we consider special power supply is your wind turbines. So you've got the different components of the wind turbine. You've got your tower. So most of the turbines in New Zealand range between 30 to 60 meters tall, with the largest standing at about 80 meters. So the generator components that house the magnetic rotor that spins within the stator, generating an EMF. Got a high-speed shaft. The shaft between the gearbox and the generator spins at a high rate in order to attain a 50 hertz supply at 230 to 400 volts. The nacelle is the other housing of mechanical and electrical parts at the top of the tower. So the top of the tower, the bulbous bit is called a nacelle. Wind vane, which monitors the wind direction, an anemometer, which measures the wind speed. You've got your controller, which processes the data being fed to it by the control and generator. Gearbox, which converts the low speed rotation of the turbine of 30 to 60 RPM to high speed of about 1,000 to 1,800 RPM. Low speed shaft, which connects to the gearbox. And the blades, big blades you see from a distance, which cause the rotor to spin when the wind moves around them. So conventional wind turbines have 3 blades, however, other systems have more. And you've got a pitch system which rotates the blades into the optimum position against the wind. And the pitch of the blades can determine the rate at which the rotor spins. And you've got a brake which stops the rotor in the event of a shutdown or emergency. Can be mechanically, electrically, or hydraulically operated. And you got your motor and drive, which moves the turbine into the optimum position in the wind. Cool. So your domestic wind turbine systems. So smaller wind turbines used as backup or supplementary power systems, and domestic are built slightly differently to the grid turbines. A domestic system may have a direct drive alternator, meaning that the alternator rotor is directly connected to the rotor of the wind turbine via a single shaft. This means that the alternator spins at the same rate as the blade rotor. Speed is not often a concern, as the domestic turbine system is a lot smaller and the blades are able to spin a lot faster. Some domestic systems produce an extra low voltage, which can then be run through an inverter, much like a solar system. The inverter then modifies the output to a state that can be used to supplement the installation's main wiring. To export back to the grid, it can also be used to charge batteries in a storage system.
Horizontal axis wind turbine from Risen Energy. Streamlined design. Low noise. Low startup speed. Small size. Easy to carry and install, running stably. A useful addition to solar energy. Power supply for boats, caravans, city lamps, monitoring, and home.
All right, so that was basically just an ad for their systems. But as you can see, the domestic turbines are a lot smaller and vary in price depending on how much power output you want. And then another special type of supply, you've got micro hydro systems. So a micro hydro system is a small hydroelectric setup. Has anyone ever seen or played around with one? I don't think they're too common in New Zealand. Good. Yeah, so it utilizes water flowing in a nearby stream or river to generate enough energy to supply a small installation, such as a house or shed. The term micro hydro encompasses all systems up to 10 kilowatt in capacity, Anything larger than that becomes classified as mini hydro, which is anything from 100 kilowatts, and anything larger than 100 kilowatts is deemed a hydro system. So one of the advantages of micro hydro compared to other systems like solar or wind is they are capable of a constant output all day, every day, as water flow tends to be fairly constant. However, a disadvantage is they are only really suited for rural areas where running streams are found on private properties. And also, a lot of local councils deem them to be hazards, noisy, ugly, I've heard, or you're dealing with streams where there may be protected or native species, in which case they don't like you putting hydro in because obviously fish. An example of a mini micro hydro system. This would be just hydro probably because it's multiple homes. As you can see, it's designed to be used alongside a river, so it's to not change the flow, but just kind of redirect it around a little bit. And it seems like they've designed they claim the turbine leaves fish unharmed. Obviously, I guess depends on the size of the fish. I hate to think what it would do to, say, like an eel here in New Zealand, especially some of the larger ones. Cool. So yeah, so you got standalone or grid-tied systems. So your standalone system or the hybrid system. So you've got your generator, your PV, your wind, which feed a battery bank, which then inverts it to the regulation conversion to AC or DC for the load. This is complete standalone. So if you want to build a house in a very rural area where you can't get power to, or it's going to be very expensive to get power to, I know some rural areas, because you have to upgrade the transformer, then run the cable and hook it in, it can be very, very expensive. In fact, there was one person posting on the community page today that their rural property had paid for a transformer upgrade because they'd bought subdivided and bought the property. But then by the time they went to hook it in years later, someone else had already gotten in and hooked it up, even though they'd paid for the increase in transformer supply. So that's something to be aware of as well for rural property. And then you've got your grid tied system, which the wind and solar go to the inverter, which go through the meter back to the grid and into your house as well. This obviously could have a battery system tied into it as well for extended use. And from what I hear, because of the solar zero crap out, the government are now going to be offering a similar scheme, but I am not 100% sure on the details because it's just what the guys have been talking about in the office here. And then you've got legislative requirements. So before the installation of such system can happen, they must be designed by a certified and approved person. So a certified and approved person must design the system. This person will know all of the specific specifications of various systems and be able to select the best method of installation so that it complies with regulatory and legislative requirements. Methods of generation such as this is considered prescribed electrical work, meaning it must be installed by a qualified and registered electrician, who also soon must have the dual generation, and I believe there's a PV endorsement on their license as well. Companies that have been doing a lot of it will be able to grandfather the system in, grandfather themselves in. Others will have to do courses, which we don't know the details of yet. There are talks about us running some, but we'll see. But all required, as stated by relevant industry standards, must be adhered to, such as earthing, isolation points, and protective devices. Labeling must be done in accordance with relevant standards also, including clear visual indications that parallel generation methods have been employed in the installation. I'm sure some of you guys have seen the massive amount of stickers that go onto switchboards as soon as you install PV. The system must be tested and comply with relevant standards as well. Testing includes effective earthing, insulation resistance, polarity, and prospective short circuit current levels. And because you're talking about generation, it's also considered high risk work. And so all solar and other generation systems must be inspected. And I'm pretty sure your backup generator systems need to be inspected as well because it's dual generation, it's high risk. Yeah. Right, so that's all of the info we need to cover off tonight. Is there anything anyone wants to ask a few questions about, go into more detail? Yeah, I know it's a lot to dump on you guys. It would have been better to do this over 2 weeks, but obviously we had to make up for Waitangi Day, unfortunately. Cool. So guys, so be sure to, because obviously you're in study mode right now, go through your Moodle stuff. The material will be available online. So if you go to your Moodle and in this special power supply, there will be a PDF. And yeah, hold on, I will post in the chat. So this is the, so basically, it's basically Tutor Stew. I'll post the YouTube video later on tonight or tomorrow, and then it will go under a playlist, which will be Year 2, July 24. And then it'll be under there, so you guys can watch the videos back as we finish. So I will stop the recording now.